Alright, so this next lesson, lesson 6. Done a couple of lessons to go. Alright, again, this interference double slit, Young's double slit experiment. So it's quite a done by Young. And so he set up a situation where he shone light through some slits, and okay, so he observed an interference pattern. So basically what we've got is we've got waves coming in here this way, so there's the wave fronts, and then because we've got narrow gaps there, we notice that from these narrow gaps we get some diffraction occurring, so we end up with kind of these curved waves. So from the top slit there we get these ones. Be nice if they used a different colour, but they haven't. Alright, around there like so. And from the bottom slit we're getting these waves here. Now remember, these are our wave crests. Alright, so it's pretty rough, but they're our wave crests, so let's get rid of all of that. Alright, so there we go. Alright, now you'll notice that there's certain spots, like here, 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 where crests are all on top of each other. So you get constructive interference, and here, here, and here. Again the same. And here, here, here. Alright, so there's all these places where we get constructive interference. And so these red lines that are on there show you the lines of destructive interference. So when you actually look at the laser and the pieces of pencil lead, the Young's double slit, that video or one of the other videos, you'll notice, as they've written there, there's some bright spots. Now, halfway in between, and here's some spots there, there, that's where we've got crests meeting troughs. And so in these places, we have a dark bit that occurs. Alright, so have a look at those videos. So the video will show you the ripple tank experiment of the interference and what you can see from the ripple tank, and then using the light. So as you can see, when you watch those videos, you get something, the light stripes, if you like, but call them that, the same as you do with the interference. Alright, so I think that's about all I need to see. So the dark bits, of course, are the nodes. Alright, so what you get, if you're looking at, is you get a fringe pattern that looks something like this. And so in towards the middle, you can, quite easily there you can see them, and then further out it's kind of a little bit darker. There's a couple there that are a bit brighter, and so on. Alright, so that's what the pattern looks like. Now, if we do an intensity graph, alright, so that's intensity up there, light intensity, you can kind of see with the light stripes, you can see they're brighter in the middle, they get duller. So that's kind of looks a bit like that pattern that we saw from the single slit. So it's kind of a bit of an amalgamation of a couple of things going on there. Alright, so let's have a look a bit further at, see if we can come up with some sort of equation. Alright, so if we're looking at a point, in this case point X, and that is a bright bit. So that's constructive interference. Alright. But if you look at the distance between here, S1 and X, and here, S2 and X, S1 to X is going to be less than S2 to X, and so at this point A here, right there, right that point there, between S2 and A, that's because S2 to X is longer, S2 to A, that's the bit of extra length. So S1 to X and A to X would be the same length. Alright, so as I've already mentioned about X, and this is the last couple of sentences there, so we've got constructive interference at X, we've got a bright stripe at X. Alright, so the path difference, that's there, the path difference, which is this bit here, S2X minus S1X, is d sine theta. Alright, and that path difference, of course, if it's constructive interference, that path difference is a whole number of wavelengths. So what we can get from that is that the path difference, d sine theta, is equal to n lambda, where n is 0, plus or minus 1, plus or minus 2, and so on. Now you might be thinking, why do we get the minus? Well, if X is over here, then there will be something over this other side here, equal distance from the middle, where there'll be a bright as well. Alright, and so that's where the plus or minus. And now the n is it's which bright spot it is. So n equals 0 would be the bright spot right here, right in the middle. And so when we go back there, way back to here. Alright, so n equals 0 is that one, n equals 1, n equals 2 is down here, and so on. Alright, let's get back to where we were. Alright. Now, also, what we have here is we've got some triangles there, and we've got this angle theta down in here, this angle theta. Now, this angle theta, you can find that tan theta, so tan theta would be equal to this, or approximately equal to that distance there, this distance over this distance. Alright, so x over L. And for small angles, and you can check this out if you like with your calculator, but for small angles, tan theta is approximately equal to sine theta. Alright, and the smaller the angle, the closer it gets. So what we can do is we can say then that sine theta is approximately equal to x on L, and so x then would be approximately equal to L sine theta. Alright, now sine theta from up here with this one here, this first one, I could say that sine theta then would be n lambda over d, and so now if I put those two things together, so taking that, putting it in here instead of sine theta, then you get that x, the distance to the nth node, is n lambda L over D, and D, of course, is the distance between, here's all what the things mean. Alright, so there's all what it is. So the angle made with the central line is theta, so that's the angle out to the fringe, whichever one it is. Lambda's the wavelength, D's the distance between the slits, N is which fringe, 0 for the middle, L is the distance from the slits to the screen, and X is the distance to the nth fringe. Alright. Right, so here's a bit straight from your notes. So there's things that it depends on. The fringe spacing is affected by wavelength, distance from the screen, separation of the slits. Okay, so change any of those things, then you will change the fringe spacing. So in the first one here, fringe spacing increases if wavelength increases, and also increases if the distance from the screen increases or the separation of the slits decreases. Alright. Bright bands, the antinodes on the screen are lines of constructive interference. This occurs when the light waves are in phase, i.e. remember the phase means whether their light stripes are the crests and troughs arriving at the same time, and the darks would be half, and there's a little equation for that. And also, just as a matter of letting you know, then that the reason for this, light stripes are excellent evidence for the wave nature, because the particle model cannot explain. The particle model would mean that particles would go straight through. So here's our things, the particles. If we've got particles coming in and we've got a screen here, those particles would go straight through and you'd end up with a couple of blobs. It's what the particle model would say. Alright, an example. Right, here's our example. Screen containing two slits, 0.1 metres apart. Is 1.2 metres from the viewing screen. Light wavelength lambda 500 nanometres falls on the slits from a distant source. How far is it between the bright fringes on the screen? So what we know is x to the xn is n lambda L. It's a bit ugly looking, isn't it? N lambda L over D. Alright, how far is it between the bright fringes? So, if we've got bright fringes here, 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 and say this is the middle, so that's n equals 0, and this is n equals 1. So, if I put n equals 1 into this, it's going to tell me this distance from the middle out to there, and because the middle is a bright fringe, and then the first one here, n equals 1, is also a bright fringe, that will tell me the distance between the bright fringes. Alright, so 1 times lambda, 500 by 10 to the minus 9, times L, 1.2, over the distance between them, and that's 0.100 millimetres, so millimetres 10 to the minus 3 metres, and when you do that, the distance between is 0.006 metres, which is 6 millimetres. Alright, so that's it. Back to the text questions now. If there's anything in there that you weren't sure of, make sure you give me a yell. Look at those videos. They're quite good at showing you what this looks like.